We're in section 9.2, two means independent samples. In this test, we collect two independent samples to test whether there is a difference in means between two populations or if one population mean is greater or less than the other. Comparing SAT scores between men and women is an example of a two independent sample test. So the sampling distribution of the difference of two means independent samples with population standard deviation unknown is Welsh as t. Suppose that a simple random sample of size n1 is taken from a population with an unknown mean mu1 and an unknown standard deviation sigma 1. In addition, a simple random sample of size n2 is taken from a population with an unknown mean mu2 and an unknown standard deviation sigma 2. If the two populations are normally distributed or the sample sizes are sufficiently large, we say if n1 is greater than 30 and n2 is greater than 30, then we can calculate our test statistic or our t-value using the following formula. Approximately follows the student's t-distribution with the smaller of n1 minus 1 or n2 minus 1 degrees of freedom, where x1 bar is the sample mean and s1 is the sample standard deviation for the first population, and likewise x2 bar is the sample mean and s2 is the sample standard deviation for population 2. Right below this we have the directions for testing hypothesis regarding the difference of two means with a TI-83 and 84 calculator. So we need to check the following requirements are met in order to perform the test. The first is that both samples have to be a simple random sample, and the second is that the two samples are independent of one another. And the third one's going to be the differences are going to be normally distributed with no outliers, or the sample size is going to be large, and that means that both of those samples, N1 and N2, both have to be greater than 30. Step 1 is determining your null and alternative hypotheses. And if you look at the null, they're all the same. Mu1 is equal to mu2. And likewise, your alternative depends on if it's a two-tailed, left-tailed, or right-tailed test. Alpha is usually given to us. And then step 3, we go to stat, test, and then to two-samp t-test. Two-samp because we're dealing with two samples, and again, we're using the t-distribution, so it's a t-test. If the data is raw, input your data into L1 and L2, set frequency 1 equal to frequency 2 equal to 1. And if summary statistics are known, make sure to input the mean, standard deviation, and sample size for each of those samples. Next, you need to highlight the appropriate relationship between mu1 and mu2. You need to set pooled to no. And you need to highlight calculator, draw, and press enter. When you do, you'll get T, which is your test statistic, and P, which is your p-value. And step 4 says if the p-value is less than alpha, we reject our H naught. And step 5 is going to be to state our conclusion, like we have been doing. On the next page, we have constructing a confidence interval for the difference of two means with the TI-83 and 84 graphing calculator. So the first thing that we're going to do is go to stat, test, and we're going to go to two-samp t int. So in order to get that confidence interval, we need to go to int, whereas testing we go to two-samp t test. So if the data is raw, you input into L1 and L2 and then set those frequencies equal to 1. And if summary statistics are known, make sure to input those in correctly. Set pool to no, and then select your confidence level. Again, your output for this will be your lower bound and your upper bound. The example right below this says, assume that the populations are normally distributed. And we have population 1, population 2. You'll notice that n for both of these is equal to 20, and that's why it's important that it does tell us that this is coming from data that has a population that's normally distributed. We also have our mean and our standard deviation for each of those samples. So it says test whether mu1 is equal to mu2 at the alpha equals 0.05 level of significance for the given sample data. So our null and our alternative, since we're testing, we need to write those down. And we're testing to see if mu1 is not equal to mu2. And like we saw in the previous page, your null is always going to be that they are equal to one another, that there's no difference. And so in order to do this test, we need to go to samp t test. On our graphing calculator, we are going to go to stat, over to test, down to samp t test. And then you need to enter in for our first population, our sample size, our sample mean, and our sample standard deviation. And then also for the second population, the sample mean, the sample standard deviation, and your sample size. Double check those numbers. And then also make sure to select the correct alternative hypothesis, which is not equal to. So mu1 is not equal to mu2. When you are done, you should get a p-value, also t, which is your test statistic. The p-value, make sure to round correct to 4 decimal places. From the calculator, we get a p-value of 0.0175, which is less than alpha, which is 0.05. And so this means that we are going to reject our null hypothesis, H naught. And so for conclusion, we can say there is sufficient evidence at the alpha equals 0.05 level of significance to conclude that the populations population means mu1 and mu2 are not equal or are different. So again, remember, you always write about, because you're testing H1, your null is assumed true unless we have enough evidence to not support it. So there is sufficient evidence at the alpha equals 0.05 level of significance to conclude that the population means mu1 and mu2 are different. Part B now says to construct a confidence interval appropriate for this hypothesis test in part A. So we're going to go ahead and draw our bell-shaped curve. Remember, when dealing with confidence intervals, they always need to be set up as a two-tailed test. So for this problem, it is already a two-tailed test since we do have our alternative hypothesis is not equal to. Since it's not equal to, that means that alpha is going to get split up into each of these tails. And so alpha was 0.05. So that means each of these tails is going to be 0.025. And again, this is because it's a two-tailed test. And by definition, that means that alpha is getting split up into both of those tails. This is discussed in chapter 7 when we were talking about confidence intervals. And so our confidence level here, since the total area under the curve is 1 minus 0.025 and the other 0.025 will give us 0.95. So I'll go ahead and write C level here is going to be 0.95 or 95%. And so in order to do this problem, we're going to go to samp t int. On the graphing calculator, we're going to go to stat, to test, down to samp t int, select enter, and then make sure you correctly enter in the values of x bar, sx, and n for population 1 and 2. And then also our C level for this problem is going to be 95% or 0.95. Make sure you select pooled to no. And from here, you'll get a lower bound and an upper bound, and we're going to go ahead and round those to 3 decimal places. From the graphing calculator, we get a lower bound of 1.298, comma 12.702. And back from chapter 8, we talked about testing when we had a confidence interval. And so what we had to look for was 0. And since both your lower and your upper bound are positive, so 0 is not in the interval, this means that we are going to reject H naught. And we can go ahead and add that up here since it is from the previous chapter. But if 0 is not in confidence interval, then reject H naught. Otherwise, you do not reject H naught. And so if you look at this, we had reject H naught using the confidence interval approach, and then using the p-value method, we also had reject H naught. So that's kind of to get us used to using the calculator and setting these problems up. The next one that we have, the next example, is more of a word problem that we would see on homework or quizzes or exams. The next example says, researchers from the University of British Columbia conducted a study to investigate the effects on color on cognitive tasks. Words were displayed on a computer screen with background colors of red and blue. Results from scores on the test of word recall are given below. Higher scores correspond to greater word recall. And so you can see we were given the values for a red background and for a blue background. Again, this is on word recall. Part A says use a 0.05 significance level to test the claim that the samples are from populations with the same mean. Assume that the criteria has been met to perform this test. So in order to do the test, we need to first set up H naught and H1, so our null and our alternative. And since we're testing that they come from populations with the same mean, I know right away that our null would be mu1 is equal to mu2. And I need to be careful here because I'm using a 1 and a 2, and I have nothing defined as what 1 and 2 are. So I'm going to go ahead and call 1 the red background and 2 the blue background. So 1 is red and 2 is blue. Make sure to define anything that you introduce. And so from here, I need to think about what my alternative hypothesis would be. And since it doesn't say anything along the lines of it being less or greater than depending on the color, it just says to test this, the alternative would be that they are not going to be the same. On our graphing calculator, we are going to go to Stat, go right to Test, and then go down to SAMP t-test. From here, you need to enter in for the red background, which is what we called population 1. Our sample mean is 15.89. We have a sample standard deviation and a sample size. And then for population 2, which is blue background, we have a sample mean, a sample standard deviation, and then also a sample size. Again, for our alternative hypothesis, we have not equals to. So mu1 should be not equal to mu2. So make sure to select that. Once you're done, go ahead and select enter, and you should get a p-value and a test statistic. From the graphing calculator and using 2SAMP t-test, we get a p-value equal to 0.0101, and our alpha is 0.05, so this is less than alpha, which is 0.05, so this means that we're going to reject H naught. And so then we need to write our conclusion. So there is sufficient evidence at the alpha equals 0.05 level of significance to conclude that and what we're talking about is the mean word recall is, and they're not equal to in my alternative hypothesis, so we'll say that the mean word recall is different for red and blue backgrounds. So part B now says to construct a confidence interval appropriate for the hypothesis test in part A. And then what is it about the confidence interval that causes us to reach the same conclusion from part A? So in order to do my confidence interval, I'm going to go ahead and draw my bell-shaped curve so I can visualize this a little bit better. Again, remember with confidence intervals, they always need to be set up as a two-tailed test. But for this case, again, since our alternative hypothesis is a two-tailed test, this just means that alpha is going to be split up into each of these little tails, and it's already then set up as a two-tailed test. And since alpha in this problem was equal to 0.05, that means that each of these little tails would have 0.25 in them. And that means our sea level would be equal to 0.95. And so in order to construct this confidence interval, we're going to have to go to 2SAMP T int. On the graphing calculator, we're going to go to stat, to test, down to 2SAMP T int. And then we need to enter in the mean, standard deviation, and sample size for each of the populations. And then also note that the sea level for this problem is going to be equal to 95% or 0.95. And from here, we're going to get a lower bound and an upper bound, and we're going to round those correctly to 3 decimal places. So from our graphing calculator, we get a lower bound of 0.882 and an upper bound of 6.278. And so since our lower bound and our upper bound are both positive, we can say that 0 is not in the interval. And since 0 is not in the interval, we will reject H naught. And so it also asked, what is it about the confidence interval that causes us to reach the same conclusion? We are looking for 0. And the reason why we're looking for 0 is because the difference, our null hypothesis, was that there was no difference between them, that mu1 is equal to mu2. So that means that that difference, if you were to subtract them, would be 0. And since 0 is not in that interval, that's why we are rejecting H naught. The next example says, researchers wanted to determine if carpeted rooms contained more bacteria than non-carpeted rooms. To determine the amount of bacteria in a room, researchers pumped the air from the room over a petri dish at the rate of 1 cubic foot per minute for 8 carpeted rooms and 8 uncarpeted rooms. Colonies of bacteria were allowed to form in the 16 petri dishes. The results are presented in the table, and it should say a normal quantile plot and box plot indicate that the data is approximately normally distributed with no outliers. Do carpeted rooms have more bacteria than uncarpeted rooms at an alpha equals 0.05 level of significance? And the reason, really quick, why we needed it to say that the data is from something that's approximately normal, from a population that's approximately normal, is because our sample for each of these is really small. It is only 8 for carpeted and 8 for uncarpeted. And so we would have to check to make sure that it is coming from a population that's normally distributed. So the first thing that we need to do is we need to set up our null and our alternative. And we can go ahead and call carpeted rooms group 1 and uncarpeted group 2. So we can say carpeted would be 1 and uncarpeted would be 2. Make sure to define those if you're going to use those. And since it's talking about the mean amount of bacteria or the average amount of bacteria, we're going to go and say that this is going to be mu sub 1 is equal to mu sub 2. And then it asked, do carpeted rooms have more bacteria than uncarpeted rooms? And again, more bacteria. And so since group 1 is carpeted, our alternative would be mu sub 1 is greater than mu sub 2. So in order to do this, we first need to put all of our data in, and we will put all of our carpeted rooms data into L1 and all of the non-carpeted rooms into L2. On your graphing calculator, you're going to go to Stat, to Edit, and then enter in all the carpeted rooms bacteria by cubic foot into L1, and then for uncarpeted rooms into L2. Double check your numbers to make sure you entered them in correctly. Next, select Stat button, go over to Test, and we're going to go down to 2SAMP-T test. And this time we are dealing with data, so make sure you select data. I selected L1 and L2 for my list, and that's where I put my data in. And then our alternative is going to be that mu1 is greater than mu2. So I'm going to select that for my alternative hypothesis. From this, I'm going to get my test statistic of t, and then also my p-value, which I need to round correctly to 4 decimal places. From the graphing calculator, we get a p-value equal to 0.1780, and this is definitely greater than alpha, which for this problem, our alpha was given to us as 0.05. And so since our p-value is greater than alpha, this means that we do not reject H naught. And so in conclusion, we can say there is not sufficient evidence at the alpha equals 0.05 level of significance to conclude. And then again, we always discuss our alternative hypothesis, and that was that carpeted rooms have more bacteria than uncarpeted rooms. So to conclude that carpeted rooms have a, we'll say a mean bacteria level. So a mean bacteria level more than or greater than uncarpeted rooms. And so since we did not reject our null hypothesis, we rejected that alternative hypothesis. This means that from this study, we showed that there is no difference in the amount of bacteria from carpeted to non-carpeted rooms. We are in section 9.3, 2 dependent samples or matched pairs data. Inferences on matched pairs data is very similar to inferences regarding population means. So matched pairs data means that you're going to be matched up. You could be matched up against yourself. And then dependent is again where one sample decides who is selected for that second sample. And so a lot of times you'll see siblings or a married couple or twins. And then matched pairs, you could also be matched up against yourself. So we could do something where we study your reaction time or your scores before taking an exam or before studying, and then after studying. So the next box that we have down here says testing hypothesis regarding differences of two mean using matched pairs design with a TI 83 or 84 calculator. So again, we must check these requirements to make sure that we can actually perform the test. And so this says that both are simple random samples. The sample data is matched pairs, and the differences are normally distributed with no outliers, or the sample size is going to be larger than 30. And again, that would be for both those data sets. Step 1 is determining the null and the alternative hypotheses. And the hypotheses can be constructed one of the three ways. Notice that we're using mu sub d, and this is going to be the mean difference in the matched pairs data. And the reason why we can find this is because that data is dependent versus looking at what we looked at before where they were independent. So subtracting these would have some kind of meaning to us. So if you look at your null, that difference in the mean is going to be 0 for all of these, and then your alternative hypothesis is going to depend on if it's a two-tailed, left-tailed, or right-tailed test. Next thing that you're going to do is look for your level of significance alpha if it's given to you, and if not, select a value. And then you'll notice that for the third step, we go to stat, test, and then to t-test, which we saw in the last chapter. And with the last chapter, t-test, it was because we were given one set of data. And we are here because we subtracted them to find that difference. And so since we subtracted them, we now have one information, one list, one thing to be inputted in our calculator. So we're going to input mu naught, which would be 0, x bar, which is going to be the mean difference, and sx, which would be our sigma. And the calculator is going to give our test statistic and our p-value. And then if the p-value is less than alpha, we reject our null. State conclusions, and this is if the sample is small, less than or equal to 30, construct a normal quantile plot, box plot to verify the differences come from a population that's approximately normally distributed. The box right below this one is confidence intervals for matched pairs data with the TI 83 or 84 calculator. The interval is exact when the population is normally distributed and approximately correct for non-normal populations, provided that n is large. The confidence interval for mu sub d is given by, and we're going to use t interval, and so this is going to be going to stat, test, and then t interval. We're going to get our lower bound and our upper bound, and then again we need to interpret our results. The example says, in an experiment conducted online at the University of Mississippi, study participants are asked to react to a stimulus. In one experiment, the participant must press a key on seeing a blue screen. Reaction time in seconds are recorded, and then the same person is then asked to press a key on seeing a red screen. Again, the reaction times are measured. The results for 6 randomly sampled study participants are as follows. Then there's a note here, and the note says that a normal probability plot and box plot of the data indicate the differences are approximately normally distributed with no outliers. This is important to note, and the reason why is because our sample is so small. So you can see we have 6 participants here. They're labeled 1, 2, 3, 4, 5, and 6. The reaction time for blue and the reaction time for red are recorded. And so what we're going to do is we're going to condense this material down into one list of data. And to do that, we're going to find the difference, and that's why it's called mu sub d. We can find the difference, and it makes sense for this experiment because we're conducting this experiment on the same person twice. So we have the reaction time for blue and the reaction time for red, and we can subtract these, and it has a meaning to the problem. It will tell us the difference in reaction times between these two colors. So when finding your differences, I suggest writing down how you're going to subtract so that way you don't make any mistakes along the way and accidentally start subtracting the opposite way. So it doesn't matter which one you want to subtract from the other. For this one, I'm going to go ahead and do red minus blue. And so when doing that, red, which is 0.408, minus blue, which is 0.582, we get negative 0.174. For the next one, 0.407 minus 0.481, it's going to be negative 0.074. Likewise, filling in these differences for the other participants. Part A says, why are these matched pairs data? And we kind of spoke about this earlier, but it's because it's the same person that's being timed for both the red and the blue stimuli. So we'll say because same person for both red and blue screens. Part B says, in this study, the color that the student was first asked to react to was randomly selected. Why is this a good idea in this experiment? So if you're asked to press a key upon seeing something, you probably are going to start to figure out and learn how to react a little bit faster as you get a little bit more used to how this experiment is going to be conducted. Just like how usually when you try something new, it takes just a minute or two to kind of wrap your head around it, try it a few times, and then you kind of adjust. And so if they start it with all the same, let's say they start everybody with blue, then by the time they all get to red, maybe they have learned from how the experiment is going. So they're going to randomize this and just randomly select. So some participants will start with blue and others will start with red. And the reason why this is a good idea is to control any learning that might happen. And I'll put learning in quotes. So learning that might take place. Part C says, is reaction time to the blue stimulus different from the reaction time to the red stimulus at an alpha equals 0.01 level of significance? And again, different is that key word in here. And so we are testing, so we need to write down our null and our alternative. And so with that said, we are testing reaction times, and so this is going to be mean. We said that it was dependent data. And so our null is always going to be mu sub d is equal to 0, so that difference is 0, meaning that there is no difference between the reaction times to the red stimuli and to the blue one. And then our alternative is going to be mu sub d is different, so it would be not equal to 0. And again, d from up above is going to be our red minus blue. So in order to do this, we need to input our differences into the calculator. So the differences, I'll go ahead and circle up here. These values need to go into L1. On your graphing calculator, you need to go to Stat, to Edit, and then enter in the differences into L1. Double check to make sure you have those entered in correct. The next thing you need to do is go to Stat, go to Test, and this time we're going to use t-test. And then you need to make sure you selected Data, and you need to make sure that you have L1 is where I put my numbers in list 1. If you put it somewhere else, make sure you label that correctly. And then you also need to set mu not equal to 0, and then select Enter. And then once you have that, you should get a p-value. Make sure you round that correct to 4 decimal places. From the calculator, we get a p-value of 0.2013, and this is greater than alpha, which is 0.01. And since this is greater than alpha, this means that we do not reject H naught. So we need to write our conclusion. And so to conclude, we can say there is not sufficient evidence at the alpha equals 0.01 level of significance. To conclude that there is a difference in reaction time to the red and blue screens. So there's one more part right below this, which says to construct a 99% confidence interval. And it says about the population mean difference and interpret your results. So if you look at your alternative hypothesis, we did have a not equals to symbol in there, which means that this is a two-tailed test. And so since it's a two-tailed test, that means that we are going to split up alpha into both of these little tails here. And so each of these little tails is going to get alpha divided by 2. And again, this is because it's a two-tailed test. And so in there, we're going to end up with 0.005 and 0.005. And so our confidence level is going to be 0.99 since the total area under the curve is 1. And then subtracting away that 0.01 from that, so our C level here would be equal to 0.99. On the graphing calculator, we are going to go to Stat, to Edit, and we're going to have all of those differences entered in L1. Next, we're going to go to Stat, scroll right to Test, and since we're constructing a confidence interval, we need to use T-interval. We do not know our population standard deviation. If we did, we would use Z-interval. And for this, we are given data, so make sure to select data. And my numbers are listed in L1, so make sure you put down whatever list you have your numbers in. And then our confidence level, or our C level, is 99. Select Enter, and you should get a lower bound and an upper bound. So from the calculator, we get an interval with a lower bound of negative 0.3789 and an upper bound of 0.1929. And so again, to test using the confidence interval approach, we look to see if 0 is in the interval or if it's not in the interval. Since our lower bound is negative, our upper bound is positive. That means that 0 is in the interval. And so what this means is we do not reject H0. And we got the same conclusion up here by doing the hypothesis test and using our t-test as we did with constructing a confidence interval. So we have one more example right below. And this one says, listed below are the heights in inches of mothers and their first daughters. The data is from a journal kept by Francis Galton. Use the 0.05 significance level to test the claim that there is no difference in the height between mothers and their firstborn daughters. And then you'll also see that it says that heights are normally distributed. Again, we don't have a large enough sample, so that's why that's important to be stated. So first question is this dependent or independent data? And the answer is that it is dependent data. Because you select a mother, you must select her daughter. It wouldn't make any sense to compare a mother's height to another child's height. So this is dependent data. And so since it's dependent and we're matched pairs, we need to go ahead and find that difference. So I'll call it D. And I'm going to subtract them and say moms minus daughters. And so the mother's height for the first one is 68 minus the 68.5. We get negative 0.5. 60 minus 60 is 0. 61 minus 63.5 is negative 2.5. And then following along with this, I'm going to go ahead and write down the rest of these differences. And so in order to conduct this test, we first need to write down our null and our alternative hypotheses. So the null is always going to be that difference, the mean, is going to be 0. So mu sub d is going to be 0. And the word that's up here is that it says there's no difference. And so that means our alternative is going to be mu sub d is not equal to 0. And so again, we need to use t-test, but in order to do that, we need to put all of our values into L1. On your graphing calculator, you need to go to Stat, to edit and enter in all the differences into L1. Make sure that you double check your numbers. Next, you're going to go to Stat, go right to Test, and then find T-Test on your graphing calculator. You need to tell it data, since we put our data into L1. You also need to make sure you set mu not equal to 0. And when you do, select Enter, and then don't forget also that your alternative hypothesis is going to be not equals to. And then you're going to get a p-value. Make sure you round it correct to 4 decimal places. So from the calculator, we get a p-value equal to 0.2013. And this is greater than alpha, which is equal to 0.05. And so this means that we do not reject H naught. And so in conclusion, we can say there is not sufficient evidence at the alpha equals 0.05 level of significance to conclude that the mean height between mothers and firstborn daughters, and firstborn daughters is different.